Hello, it's Keith here, and this is lesson 10 of the basic series of my programming tutorials. In this series we look at the basic concepts and we discuss them, and today we're going to be discussing sound terminology. Now this chapter, as always, is based on the content of my book, so if you want to support these tutorials and get this in print, please buy my book. But what we're looking at today is sound. Why are we looking at it? We're going to be discussing the terminology. You're going to need to know it if you're going to be reading hardware manuals. If you're going to program an AY chip or an FM synthesis chip of your 8086, you're going to need to understand some of the concepts in there, and if you don't know anything about sound and music, you're going to struggle to understand some of it. I certainly did. So what we're doing today is an idiot's guide to sort of sound terminology. I'm the resident idiot. I'm going to be telling you what I had to learn along the way, so I apologize if I'm oversimplifying things or I'm explaining things wrong if you know this kind of stuff. But if you know this kind of stuff, why are you even watching this episode? Anyway, we're going to go over the concept, and you can see above me we've got an oscilloscope, and I'm hoping this is going to help us out with some of those concepts. Now the first thing we need to discuss is the actual shape of waves. That's what that thing's doing there. So let's go over to our theatre screen over here, and let's have a look at this image here. So here we've got a sort of imaginary waveform that you might see on an oscilloscope or on Audacity as well. It's great for looking at waveforms. So this is what you might see, and there's some terminology you might come across. Now one of them is amplitude. There's two ways you may see this. There is the general amplitude, which will be the height from the middle of the middle line, which is 0. So that would be referred to as amplitude. You might also see peak-to-peak amplitude, which is the distance between the top and the bottom. This is basically the volume. So the simple term you will be familiar with is volume, but you might hear this called amplitude. Now the other one you will probably need to know about is the concept of the wavelength. Now this is the distance between 2 points on the wave. So the wave goes up, then it goes down, then it returns back to the same point. So this is the known as the wavelength, and this is effectively the pitch. Now if we just go back to my other screen so that we've got my oscilloscope here, go away Chibico, we've seen you already. If I talk quite loudly, you'll notice the waves get very high. If I talk very quietly, you notice they're quite low. So this is the advantage of having some kind of oscilloscope. The oscilloscope I'm using is Frequency Analyzer, which is free, but unfortunately it doesn't work with some sound cards because the rotters at Microsoft have removed the what you hear function from their sound drivers in Windows 10, so I can't get it working. I've actually looped through my two sound cards, but if you use Audacity you might have more success. If you've got a microphone, things like that, you can record and then look at it, play it back. You can even change the pitch of it and things. So the height of the waves is the volume and the width is the pitch. So if you record a low tone, you'll notice the wave is very wide. If you record a high tone, the wave is very short. And that's what you can see in this image here. So as I say, if we've got a loud tone, you'll notice very tall waves, so nice tall waves here. Quiet tone, short waves. If the pitch is high, the wavelength is very tight. If the pitch is low, you much longer waves here. So there we go. So that's what we're seeing. I think that kind of thing, knowing that's how the waves will appear, is quite important when you come to do sound, especially on a system like the ZX Spectrum or beeper systems, where we're actually physically generating the wave one bit at a time. But it's also useful for things like if you're doing digital sound sampling. Understanding them is very helpful, and as I say, oscilloscopes or wave representations in a program like Audacity is very useful. Now, depending on the system we're working with, we will have a finite number of common waveforms we might see. So let's just copy this image and let's put it into our screen over here. Let's see. So we're going to look and we're going to hear a variety of different tones. So the sine wave is a very smooth wave, a very curved wave here, represented by the sine function, of course. And this is a tone that's used by a lot of FM synthesis systems. Older retro systems like the AY are big on the square wave. A square wave is a very uniform pattern. It goes up for a period and then down for the same period. Another one that's used by the C64 or the SID chip is the triangle wave, which is a triangle, a kind of zigzag, very even again. Similar to the triangle is the sawtooth. This is it's sort of lopsided. It's similar to the triangle wave, but again a zigzag. Now the pulse wave and the square wave are kind of similar, but the difference is that the pulse wave only goes down for a short period and then goes back up, whereas the square wave, the frequency is more uniform there. And then finally is noise, which is a distortion effect, so very random pattern here. These were all captured with the oscilloscope software, and then I've drawn them into this graphical representation. Now what we're going to do next is we're going to actually hear them in Audacity. So we're going to hear each of these sounds one at a time, and these were recorded on emulators emulating the real chips, so the sounds should be representative of what the actual hardware would do. So first of all, let's hear the sine wave here. So a very smooth tone there. You could see it being represented up there, and if we zoom in you can see a very smooth pattern there. So that's the sine wave. Next is the square wave, which is the AY chips staple, so to speak. So a much harsher tone there. You know, it's still a good tone. It's one I grew up with the AY chip, so I'm very fond of it, but some people won't prefer it. And then here's the triangle wave, as I say, a triangle, so very obvious why it's named that. So a much more soft tone than the square wave. It's more similar to the sine wave. And then the sawtooth. Now this one is very different. It's the kind of opposite orientation to this one here, but again it's the same concept. So a more buzzing, a harsher tone again, and then the pulse wave here. Again, let's say this is much more similar to the square wave here. So we've got just these blips, as opposed to the square wave, which has this very uniform pattern. A quite harsh tone there. Interesting, actually. Just play that again. It seems the representation is inverted compared to the oscilloscope above me. I don't know why that is, but anyway. So that's the pulse wave, and then finally the noise, which is literally random data. You can see there, very random. Depends. The noise effect on different sound processors will vary depending on how the randomness is generated. There we go, very random sound there. So that's a variety of sounds and how they appear as waves, and you can go to my website and you can download all of those sound samples that I have just played, if you can get them all just here. So you can go and download those yourself and have a look at them in your own software and just sort of satisfy yourself what they look like and how they sound, and if you want to play with them and change the pitch and things, you can do that. Now we did just briefly discuss beeper sound. Now beeper sound is basically where the sound hardware itself doesn't really have any functionality of its own. We just have a volume bit, or 1 bit, sometimes 5 bits depending on the hardware. We can set the level that the sound is currently outputting. Say sometimes it's just 1 bit on and off, and we have to manually form one of these waves as a combination of on and off bits. So for example, with the square wave here, you could probably imagine how we could create that as a combination of ons and offs. If we only have a 1 bit to beeper though, we are going to struggle to create a triangle wave though, because we would need multiple levels to do that, and a sine wave is also going to be impossible. And for noise we would just randomly turn it on and off. But that's the most basic of the sound hardware, beeper sound, but it's perfectly usable if that's all you've got. Now the term PSG stands for Programmable Sound Generator, and that is just basically the more advanced sound chips that can create more advanced sound, like systems like the Amstrad CPC, the BBC, the Commodore 64, a variety of different things. It's really a very generic term for early sound processors. The more advanced one is frequency modulation, and this is where multiple oscillating sound waves are combined to create more realistic sounds. The advantage is they're more realistic. The disadvantage for idiots like me is it's harder to make sounds because we need to configure a lot more working parts to build the sound together. An honourable mention, I think, needs to go to mod tracks and wavetable synthesis. It's a bit hard to know exactly at what level you want to call something wavetable synthesis. Wavetable synthesis is basically where you take a variety of sound samples and you combine them together. It's a bit tricky because I've seen the dictionary definition of wavetable synthesis being a large number of very small sound samples combined with other effects to build a sound. However, in a lot of cases, a lot of hardware defines wavetable synthesis as simply being using a sound sample, a single sound sample, and changing the pitch of it to make a note, which is a perfectly viable way of making sounds, but vastly simple compared to what I would consider wavetable synthesis. I would consider it to at least need multiple sounds being used to make a full range of the of a musical keyboard range of octaves, but in a lot of cases it seems to be used to refer to just a simple sound sample. In the case of the WonderSwan, it literally just uses a 32 sample sound, and they call that wavetable synthesis, and I really couldn't call it that. Now, mod tracks are the old Amiga music files, very good. I used to love listening to these. They allowed for using sound sampling and changing the pitch of those sound samples by speeding up and slowing down the samples. They gave a good range of simple music and were relatively small, just a few hundred kilobytes, but gave a great, not CD quality sound, but something comparable. Now, we're going to go over a few other concepts now. The first one is total level, which is just another way of calling volume. So if you see total level in the terminology of the documentation you're reading, you can just exchange that for the word volume, and that's what it means. Of course, channels, in most cases, are referring to multiple playing instruments. Sometimes these will have different positions. If your sound hardware has 3 channels, you can be sure you can play 3 samples at the same time. Sometimes one will be hard left, one will be hard right, one will be hard center, and sometimes you can configure those to be at different panning positions. But as I say, you can be sure you will be able to play multiple things at the same time if you have multiple channels. Envelope, this is the reference to sound changing across time. How the sound changes will depend on the hardware. In a simple sense, it's usually just the volume, and this allows us to make sounds that will change over time. For example, maybe we want a sound that starts loud and then quickly fades out, or maybe we want one that pulses in and out, or one that fades in. This will depend on the hardware, the options that are available. You will usually turn the envelope on and select the envelope for one of your channels. This is based on the AY hardware, so these are the options available on that. Other systems have other options, and some have no options at all. The other thing is that envelopes don't necessarily mean volume. It can also affect the pitch, so it's simply the applying of a function across time, not necessarily to volume. Okay, so those are concepts that you will frequently see on the more basic systems. When you come to the more advanced systems, you start to hear some more complex concepts to how the sound will change across time, and these are related to, I think, best thinking of a piano keyboard. Now, I've never really played a piano keyboard, but I do know how the sound is affected by how you press the keys. I used to own a synthesizer, and I know a little bit about the internal workings, enough to explain this, hopefully. So, if you think of your piano keyboard, if you've ever come across one or a synthesizer, you will know that the way you press the key and the way you release the key affects the sound that is made. Now, in the physical workings of a piano, basically the way it works is there is a string, and the key, when you press it down, there is a hammer that hits the string and the string vibrates. When you release the key, there is a damper, and this touches the string and that stops the string vibrating. However, all of this doesn't happen in instants, so there is changes to the tone across time. Now, the more advanced FM synthesis type synthesizers will, by synthesizer I mean the hardware that our computers may have, will allow for this to be represented. And this is all based on 2 time events, one that is the key down, known as K on, for key on, and one that is the release of the key, known as K off, which is key up. Now, the K on will be the start of the sound, and the K off will be the time that the sound starts to diminish, but it doesn't necessarily mean the time that the sound stops. And we can configure in each of these stages and have the sound affected in different ways. And this is just a basic representation I'm showing here. The actual stages and the configurability will depend on your hardware, but you need to understand each of these stages to be able to read the documentation of the hardware you're actually trying to program. So let's imagine that we've pressed a key on our piano keyboard. Well, the hammer will hit the string and you will get an attack phase, and this is when the sound rapidly increases. So it might rapidly increase in loudness, and that is the attack. It will happen very fast, over a fraction of a second possibly, and then it will reach a peak, and for a short period of time it might quickly drop off from that, and that is known as the decay stage. All of this time the key is still held down. Now, at some point, the string will probably reach a sort of constant resonating tone, and that is the sustain phase. So the initial drop-off after the initial attack has ended, and it's now reached a more constant level. Finally, when the player releases the key, the damper will hit the string on our physical keyboard, and the release stage will occur, so the damper is silencing, and that will happen very quickly. Now, the length of each of these phases and how the sound changes will depend on how we want to configure the sound hardware. So we could have a very long or a very short decay stage. We could even have no decay stage. We could have the sound reach 0 during the decay stage, or we could have it reach 50%, 90%. Just depends what kind of sound we want. And equally with the release stage, we may want the release to be very long, or we may want it to be instant. The same with the attack stage. So as I say, I'm just showing you this so that you understand these concepts, because when you come to read your hardware and when you look at your hardware registers, you will see you've got an attack value in some cases, a decay value, a sustain value, and a release value. And if you configure them wrong, you may get no sound, because if your attack is 0 and your sustain is 0, your attack level and sustain level, you may end up with a sound that never plays at all. So you do need to have some kind of understanding of these concepts to be able to configure your sound hardware. That's why we're discussing them today. So there's a few more things we need to discuss. The next one we're going to discuss is the concept of generators, because you might hear this term referred to, and you'll have frequency generators, noise generators, and envelope generators. Now, this is just the reference to the parts of the sound hardware that are producing signals that can be combined together to produce the eventual sound. So we might be given ability to turn on these various generators and combine them together. So again, it just concepts that you might hear, and you might be a bit alien to you. Or what is a noise generator? I can see I've got an option for it. Why would I need that? Well, it's about being able to configure and enable those components that might be combined to channels to turn the sound effect on. As I say, though, it's all very hardware specific, so I can't give you specifics for one piece of hardware in this tutorial. I do have platform specific tutorials. If you look up Chibi Sound, it's a little sound driver I create on all of my systems that creates basic sound effects. Now, another term you might hear is LFO, which is the low frequency oscillator. This is for creating very low sounds, very low waveforms. This could be for the pitch, but it could also, again, be for panning or volume. Again, just entirely depends on the sound. Now, another thing that is a little bit odd on some systems like the Game Boy and the NES is not all sound channels are created equally, and you might hear some of the channels referred to as tone and sweep channels. These have extra functions which allow the sound pitch to change over time. You can make them bend up and down, and so you can create different sounds. Now, you can also turn this kind of functionality off so that you can have two sound channels that create an even constant sound. But if you are wanting to create more complex sounds, you might need to use the more advanced tone and sweep channel to create the more complex sound with that variation, and use your regular channel for the simpler sounds. As I say, there's a lot of variation in the hardware and even in the channels on the hardware. Often you will find certain channels can do certain things and others can't. Sometimes only one channel can be turned on to do noise. Sometimes only one channel can use the envelope. Entirely depends on your hardware. Now, one other thing that we're going to have to discuss, because again, it's something that I struggle with, and you do need to know about it in some hardware. You might just want to create very basic beeps, but your hardware may not allow you to do that. You may have to understand the concept of the octave, because some of the hardware does work in that format. So I did play music when I was young. I wasn't very good at it, and I've forgotten it all by now, but you might need to know how the octave works from the point of view of how, maybe you need to read it from music, or maybe you just need to understand the piano keyboard and understand what notes exist and what don't. So basically, if you've got a printed octave, it will appear like this, and if you've got a piano keyboard, you will have letters C, D, E, F, G, A, B, C. It's called the octave because there are 8 keys between each following letter, so C to C is 8. Now there are sharps and flats between C and D, D and E, F and G, and A and B, but there is not between E and F. So depending on the hardware, you may not be able to create a between sound on that. And just for completeness, I will point out that C sharp and D flat are the same note, and they are halfway between the two, and that's the black keys on your keyboard. So in case you ever need to see that, or if you need to read a piece of sheet music just to understand how to represent the notes within in your software, maybe you're trying to convert a piece of sheet music and make the music in your game, those charts are just there for you to help you out if, like me, you can't remember them. So there you go. Now, another concept that comes in with some of the more complex ones, the FM synthesis chips, is operators and connectors. Now, within these FM synthesis chips, you have multiple frequency waves that are being combined together to produce the final sound. And so basically, you then have operators, which are calculations that are being applied to these different sounds. Now, again, if you're just getting started, you probably just want a simple sound to play, but you have to configure these kind of things to create the sound. And so you will need to configure multiple operators and a connection to combine them together. And here I've shown two basic ones. These are from the AdLib sound chip. The AdLib 1 sound chip had these. I think with AdLib 3, OPL3, they added more. So again, you will need to see the documentation and you'll need to see which ones you want, and you'll need to try different ones and see which gives the sound you need. But as I say, basically you will need to select something because otherwise you will have no sound. And depending on how you've combined the operators together, and you will need to make sure you give the settings of those operators viable values, otherwise you will never end up with any sound coming out. You might have configured operator 1 fine, but as that passes through operator 2, you could still end up with silence. Something to bear in mind there. Now, the next thing we're going to discuss, and I did cover this on my Z8 tutorials, is the concept of digital wave files. Now, you can see above me we've got a digital wave. It's a very high resolution digital wave, but it is digital. How can we convert these to play them back on early hardware? Well, it's going to entirely depend on our hardware, of course, but there's some things that are generally true. Now, if we look at this example here, we've got a wave file that I took a screenshot of with Audacity, I think I used for that. And this is a wave sample, and this on modern hardware can be stored as floating point, which means the middle line is a value of 0, the top value is 1, and the bottom value is -1, so floating point. Now that is if it's floating point, but that can be converted to a signed number. And so if we were storing as 16-bit signed, we would go from 3267 positive to -3268. So that is the same representation. So the same wave could be stored either as 1 to -1 or 32767 to -32768. Now, if we are using lower resolutions, which are what we're probably going to want to do for our early hardware, we're probably going to work in 8 bits. And so we would go maybe 8-bit signed, 127 to -128. But again, we just need to convert the values that we read in from our wave file or sampled into those values for the signed number. Now, if we're working unsigned, instead of -128 to +127 with a middle value of 0, we would instead use 255 to 0 with a middle value of 128. Now, that is going to be fine for some systems, but what about our early systems that really can't play wave files at all? Amstrad CPC, for example. Well, it may surprise you to know you can actually get basically any system, even the humble ZX Spectrum with its 1-bit beeper sound, to play digital sound files. And if you played those old systems, you might have heard like your Treasure Island Dizzy would speak to you, a bit distorted, but it would speak to you. And the way they would do it is you would convert these unsigned values into the bit depth of the final hardware, the volume level of the final hardware. All we need to do to rebuild our complex wave file is set the output volume very quickly to rebuild that wave file accordingly. So if our system like the Amstrad CPC has a volume level that's 4-bit, we just convert this 8-bit unsigned to a 4-bit value from 0 to 15 with a middle value of 8, and then we set our volume level of our channel and it will play the sound. And if our system is even lower than 4-bit, just 1-bit, well, we just toggle between 0 and 1, and again we can recreate the sound. And you can play digital sound files on the ZX Spectrum, and I have tutorials that have done that. Okay, so that's how you can use even the oldest of hardware to create digital sound samples if you so wish. Now, more advanced systems frequently use a format known as adaptive PCM. Now, this is complex and the algorithm used will vary depending on the hardware. So I'm going to just discuss it in a very simple way using a hypothetical algorithm here. Now, the purpose of AdPCM is to solve a simple problem. If we've got a 16-bit sound sample, we can reduce the quality by lowering the frequency, which will make it more muffled, but we might also want to reduce the bit depth. Now, we could just simply save it as a 4-bit sample, but that would become heavily distorted. what Add PCM allows us to do is it allows us to take what we know about wave files, that they go up and they go down, and they don't change very, very quickly in a lot of cases. It's a relatively smooth curve. And so Add PCM attempts to use just 4 bits to represent the movements of a 16-bit wave. So we get almost the same quality as 16 bits with a quarter of the bit depth. And while that might seem an incredible attempt, it is actually very possible. It's very hard to tell the difference of the sound samples in actual cases. Now, how does Add PCM do this? Well, the way Add PCM works is it will have a table of possible move sizes. So as our wave goes up and down, the amount of difference from the current position and the next position will be some kind of value. So maybe +1 or +128 or -1 or -128 and so on. Now in our +32767 to -32768 range, we will have a very, very large range of possible changes. And so what Add PCM does is it creates a table of possible move sizes. And so here is my imaginary table here, but the actual table would be much larger, and it would have usually far more than 16 values. So it would maybe have 32 values, and these would be all the way from maybe -32768 to +32768, but they would also contain very, very small changes of -4 and +4, -1, +1, things like that. Now, because we're only using 4 bits for our Add PCM values that are being stored in memory, we can't use the full range of the table for the move between each sample in the sample we're trying to record. So what we actually do is we move the potential range of values within our lookup table depending on the last one. So if the last move was very large, we will try and use the largest one within the range within our lookup table, but we will then move the potential range for the next sample that we look up to compensate for the fact that the last one was too small. And so over a few samples we will eventually end up at the right position. Then if the change in the wave becomes very small, we will only for a short period be able to make very large moves, but then the range of lookup values that we're considering will go back down, and we will then be able to make very fine changes again. As I say, the Add PCM step table will usually be relatively large. It will contain probably dozens of values. But because we're using a value 4 bits, we can only consider a range of those values. So that's how it tends to work. Now, the exact algorithm will vary depending on the hardware. You can write your own software algorithms. I did use one. And another curious thing with Add PCM is while it's really intended for sound, you can use the concept for other things. I actually had a very early digital camera which used Add PCM for photographs. Quality was quite poor, quite grainy, but it did work. And as I say, if you've got a case where you need to compress video or images, you can't use JPEG, you can use Add PCM if you so wish. So it's a very interesting concept. I've only described it extremely crudely here, and I probably haven't done a good enough job. You would need to go into some quite detail. It would be something I'd have to really do a full tutorial on. So I just wanted to explain to you what the concept was. It's a very good audio format for 16-bit systems or more. It's not really useful for 8-bit systems, but there we go. Now, the final thing I just want to quickly mention is I/O ports and joysticks. Why am I discussing I/O ports and joysticks in a sound tutorial? Well, that's because some systems like the AY sound chip, they had I/O ports connected to them. So quite often those ports were used for things like joysticks. So don't be surprised if you're reading your audio documentation and you hear joysticks mentioned. And also on some systems like the Dragon Tandy Coco, the analog to digital converter that was used for the audio was also used for reading the joysticks. So sometimes these things cross over. So just bear it in mind, and don't be surprised if you see I/O being discussed in your sound documentation. Anyway, that's all we're covering today. So if you like what you've seen, please like and subscribe. As I say, if you want to know more about audio, please look at some of my other tutorials. I've covered all kinds of things. So if you search for Chibi Akumas and the system you're interested in, I've probably covered it because I've done most of these. All of the hardware I cover, I've written my Chibi sound driver for, which is my simple sound driver. Anyway, I hope you've enjoyed this today. Thanks for watching, and goodbye.